So we're looking at page 50 related to the chain rule for multivariable functions. So z is equal to f of xy, given that f of xy is equal to the square root of x squared over 4 plus y squared. But we also have the parameterization in terms of s and t, where x is equal to 2t cosine of s, and y is equal to t sine of s. All right, so what we need is the derivative, the partial, with respect to s of the original function and also with respect to t. Okay, so the first thing that we would want to do is find the partials with respect to the given variables within the multivariable function. So I would be looking for partial z with respect to x, then also partial z with respect to y. Before I even get started on that, I'm going to rewrite as z equals this, the square root, I'm going to write it as x. Actually, let me write that as 1 over 4x squared plus y squared to the 1/2 power. So my first order partial with respect to x is going to be 1/2 1/4 x squared plus y squared to the negative 1/2 multiplied by the derivative on the inside with respect to x is going to be 2/4 x, but that's really just 1/2 x. All right, so I have that. Then I need my first order partial with respect to y. I have the same ingredients, except we're taking the derivative of the y part of it, of the inner component of the function. Derivative of y squared become 2y. All right. Now, for the sake of organization, you may want to make a tree diagram, just so you can kind of see how this flows. We're starting off with z, and we're breaking that into partials with respect to x and y, and then we're still dealing with multivariable functions. So when I take the partial of x, I could take that with respect to s or t. So partial x with respect to s, partial x with respect to t. The same thing with y's. All right, so this would be a set of possible pathways to a set of derivatives. All right, well, what I want to do is first focus on partial z with respect to s. All right, so if we think about that, that would be the product of these two. All right, because partial z with respect to x times partial x with respect to s, just simple multiplication, cancel, you get partial z with respect to s. We do have another pathway to get us to partial z with respect to s, though, and that would be, started highlighting it, but it's in the wrong color. Partial z with respect to y and partial y with respect to s would get us to the same partial derivative. So partial z with respect to y times partial y with respect to s, cancel, and you get partial z with respect to s. So it could be one pathway or the other. All right, so it's the first pathway or the second one. All right, so this really is a tree diagram, or a decision tree, however you want to think of it, but it's probability based. All right, so we're looking at a sample space of all different partials that make up the set of multivariable functions. Whenever you're dealing with choice in that regard, we would apply the addition and the multiplication rules that we would use in a probability class. All right, so aside from needing to get all my first and second order partials, first order partials for both z and x and y, I need to organize them in the appropriate way. All right, so for this, I actually need everything that I have here in order to come up with partial z with respect to s. So I'm just going to kind of reorganize it a little bit. Get rid of these because I'm actually going to use this information, because I can't just conjure up a partial z with respect to s just out of thin air. So what I'll do is I'll use these different components, add them together, and that'll ultimately give me partial z with respect to s. All right. So what I can then do, or what I would then need to do, I should say, is get my partials for, I need x in terms of s and y in terms of s. All right, so partial x in terms of s, partial y in terms of s. Okay, so x in terms of s, that's actually not too bad because 2t is treated as constant, or a constant multiple. So I just need the derivative of cosine s, which would be negative sine of s. All right, so negative 2t sine of s. And I need the derivative of this, t sine of s with respect to s. T is treated as a constant multiple, stays put, you bring along for a ride. Derivative of sine of s is cosine of s, so t cosine of s. All right. So then it's just a matter of putting it all together in the right order. So partial z with respect to s. Yeah, I might have mentioned this. I usually try to. At some point, my deltas start morphing into things that look more like 2's. These are all of these supposed to be deltas. All right. So partial z with respect to x, that's this, multiplied by partial x with respect to s, that's this one. Little multiplication symbol in there. I'll do it in red. Plus partial z with respect to y, multiplied by partial y with respect to s. All right. So I'm just going to move some stuff around, and that would be our derivative. There's no indication that we need to simplify, so I'm not going to bother. If you wanted to, by all means, but not something I'm going to require of you, because obviously this is enough work as it is. All right. So the next layer of this problem is asking us to find partial z with respect to t. So if you just follow the pathways that would get you there, partial z with respect to t, I'm going to turn off my line draw tool. Still looks way too much like it too. Partial z with respect to t. If we follow the pathway that gets us down to a t, we would start off the same place we started off previously, and we'd follow the road less traveled, I suppose. So I'd be working down this branch or pathway. All right, those products would still bear out. Partial z with respect to x, multiplied by partial x with respect to t. Partial x's cancel away, you're left with partial z with respect to t. Same idea for the y's. All right, so we'd be looking for partial, again, z with respect to x times partial x with respect to t plus partial z with respect to y multiplied by partial y with respect to t. All right, so I'm going to get a little sneaky here. I'm going to take all of this stuff, copy, paste. I'm going to get rid of all the stuff that's going to change. So it's with respect to t now. I can make that change immediately. These derivatives would change. This one and this one. All right, and so then right up over here, I just compute partial x with respect to t, partial y with respect to t. All right, so going back to my x equation, with respect to t, cosine of s is thought of as a constant multiple. Derivative of t is 1, so this just becomes 2 cosine s. Partial y with respect to t, that's this bad boy over here. T is treated as the variable, sine of s is now treated as the constant multiple, so hang on to the sine of s. Derivative, again, of t goes to 1, so sine of s would be my derivative. And so this would be the chain rule expansion of the derivative, the partial derivative of z with respect to t. Now, you could simplify, but there really is no need to. In fact, what some people will do, and I've even seen this in textbooks, they'll go now and replace all the x's and y's with the functions that define x and y and simplify. But for that, I would say, well, if you're going to do that, why not make that substitution initially and forget about the chain rule? Right? So the whole idea here is to have a derivative that's in terms of all these other variables. Right? So perhaps it's more convenient that way. Who knows? All right? It's just another option. All right? In fact, you look at this derivative here, which is with respect to t, you see that there isn't even a single instance of a t in the derivative that is supposedly with respect to t. So it's very interesting, but also it can be a little confusing if you don't have an organized approach.